So now we want to look at homework problems 2 and 3. And to look at these, all right, what we're going to do is we have to introduce just a little bit of background physics before we actually solve anything. Okay, so what we're going to do is introduce the idea of centripetal acceleration. And the idea of centripetal acceleration, okay, and we call this F sub c, all right, and this is centripetal acceleration. Okay, now acceleration, all right, is simply a change in your state of motion. Okay, so acceleration, the definition of acceleration is a change in the state of your motion. Okay. So anytime you speed up or slow down, let's say you're driving on a straight road, okay? Anytime you speed up or slow down, that changes your state of motion. But also, if you go around a curve, okay, if you go around a curve, you're also changing your state of motion because your direction is changing, okay? And so anytime you have a change in your state of motion, now Newton's first law of motion says an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by a force, okay? And in some cases, your force can be centripetal in nature, okay? And so what acceleration does is it causes you to change that motion. Now there's a word in there that I left out, and that word is uniform. So an object at rest will stay at rest, and an object in uniform motion will stay in uniform motion. What that means is motion in a straight line at a constant speed. Okay? If I put something into motion, then it will move at a constant speed in a straight line unless something acts on it that exerts a force on it. Okay? And you can imagine, go out into space, right? Go out into space, go away from gravity, go away from all of the known planets and stars and galaxies and everything. Just go out into empty space and fire an arrow from a bow. That arrow will never ever slow down, right? It'll just keep going and going and going until something acts on it, right? Until something exerts a force on it. And remember that a force can be thought of as essentially a push or a pull, okay? If I push or pull on something, then I'm exerting a force on it, okay? And so centripetal acceleration is the type of acceleration that describes curvature, okay, curved motion. So when you speed up or slow down, like you're coming up to a stop sign or accelerating from a stoplight, right? Usually those, at least over short distances, are straight, right? Your motion isn't curved. Whereas your curved motion, let's say I'm going around a curve in a road, or I take a turn on my bicycle, those types of things. Those instances where you're turning as you're moving, the concept of centripetal acceleration now applies, okay? Now, one more thing, Newton's second law of motion says that a force is equal to an object's mass times the acceleration that it experiences, okay? An object's mass times the acceleration that it experiences. So if I exert a push or a pull on a mass, so the m is the mass that's experiencing the push or pull, okay, your m is your mass that's experiencing the push or pull, and a is the acceleration that mass is experiencing. Okay? And so, anytime I give a push or a pull to an object, I cause it to accelerate, and that force that I exert will be equal to the product of the object's mass times the acceleration that I give it. Okay? Now, what does all this have to do with centripetal acceleration? So let's just imagine you traveling around a circular track. And let me maybe even try to draw a better circular track. That was terrible. Right? So let's say you're just traveling around a circular track, right? You're just going around the track this way. Well, you're constantly changing your direction, right? You're constantly changing your direction. And as you change your direction, you kind of feel pushed outward, right? So what exactly is happening? Why do you feel pushed outward? Well, it's because, let's say that you start at this point right here, right? And at that point right there, if you're moving around a circle, your instantaneous direction of motion is straight ahead, right? Your instantaneous direction of motion is straight ahead. But a short time later, you're here, and your instantaneous motion is also straight ahead, but that direction has changed, right? Your direction has changed. And the direction that you have changed is actually inward, but you feel thrown outward. Okay, so that's why you feel thrown outward. Okay, so now, what does this have to do with gravity, right? How can we solve these types of problems? So one of your homework questions asks, what is the circular velocity of a satellite (7,000) let's call that meters. Sorry, 7,000 meters. No, let's call it kilometers. Okay. What is the circular velocity of a satellite 7,000 kilometers above Earth's surface? Now remember that Earth's radius, let's call it R sub E, is equal to 6,371 kilometers. Okay, so Earth's radius is equal to 6,371 kilometers. Now, here's how this works. So let's say this is the Earth, and there's your radius of the Earth, and the satellite is going to orbit somewhere out here, and the satellite is 7,000 kilometers above the surface. Okay, now here's the key. Okay, here's the key. The formula for centripetal acceleration is equal to the speed that the object travels. We call it v. Technically, v stands for velocity, but in our case, we can use v. Okay, so the square of that, let me clean that up, the square, v squared over r, where r is the distance from the center of rotation. So in our case, the distance from the center of the Earth out to the satellite's orbit is our actual total r. Okay, so in our case, the total distance is from the center out to the orbit, so that means we have to add those two distances. Okay, so the radius of the Earth, sorry about that, a flub up of technology. The radius of the orbit will be the sum of the radius of the Earth plus the distance from the surface of the Earth out to its orbit. Okay. Now, this is the acceleration, and so the force is equal to the mass of the satellite times its acceleration, which is v squared over r. Now, here's the key. Okay, so this is the centripetal force that is describing the motion of the satellite as it's orbiting around the Earth. Okay, but here's the question. What is the actual force causing the push and pull on the satellite? Well, the answer there is the force of gravity. So that tells us that the force of gravity between the Earth and the satellite is going to be g times the mass of the Earth times the mass of the satellite divided by the distance between them squared, the distance between their centers, really. Remember that r is the distance between the centers of the objects. And so the r here, that is the distance from the center of the Earth out to the orbit, is also the same r that's here. And so what this means is we can actually set these equal to each other. So the F centripetal must equal the F grav. And that means that we can actually then set these equal to each other and solve for the velocity. Okay? So when we come back to our question here, what is the circular velocity of a satellite 7,000 kilometers above Earth's surface? Well, all we do is set these two equations equal to each other, and then we can solve for v. So I'm going to say ms, the mass of the satellite times the velocity squared divided by r, is equal to g times the mass of the Earth times the mass of the satellite divided by r squared. And I want to solve for v. Now, first things first, notice that the masses of the satellites cancel out. They appear on both sides. As well as an r cancels out. So I'm left with v squared equals g times me over r. And to undo the square on the v, I take the square root. So now I just have to plug in the values for these. And remember that r is going to be 6,371 plus 7,000. So r, the total r, is going to be 13,371 kilometers, right? So 13,371 kilometers is my total r. And so what this is going to give me, and again I'm going to drop units for the sake of brevity, 6.67 should be very clear here. 6.67 times 10 to the negative 11 times the mass of the Earth, and recall we said the mass of the Earth the other day was 5.98 times 10 to the 24 kilograms. That doesn't look good. There we go. 5.98 times 10 to the 24 and divided by 13,371. Okay. And I may need to check that. Is it 6,371 or is it 6,731? In any case, you can look up the radius of the Earth. And in fact, let me do that right now.